Hello, welcome again. So far, we have looked at time response of first order systems and second order systems. For the first order systems, we saw that there is only one pole which is located on the real axis. So when we looked at the time response, the time response was dominated by an exponential term. And the main consideration that we saw was that based on the location of the poles, we will end up having either a faster or a slower response. For the second order systems, we analyzed the time response and we saw that there are many possible cases. We can have a undamped system, we can have a underdamped system, critically damped, or a, or overdamped system. Based on what kind of system response, based on what kind of damping the system had, we ended up having different kind of responses out of the system. So first order system, the response was a little simpler to analyze. Second order system, there were a little bit more complications. If we think about in general, it is quite natural that systems can be represented by not just first order and second order, but higher order systems also. So how do we analyze this system? It is sure that the analysis of the higher order systems is going to be more complicated than the analysis of the first order and the second order systems. But often when we are trying to analyze these higher order systems in practice, we are often looking for opportunities where we can approximate them using either a first order or a second order system. So over here, it is said that if you look at the topic, it says a higher order system can be approximated by a second order system if there exists a pair of a complex dominant poles. Actually, the same thing can also hold true for respond for approximating a higher order system by a first order system. So a higher order system can also be approximated by a first order system if there exists a real dominant pole for it. So let's look at what it means by the dominant poles. So I described earlier that if we look at the pole zero map, so if we plot all the poles, if the pole has a real part which has a larger magnitude, so a pole if a pole goes more towards the left half plane of the complex plane or goes further away from the imaginary axis, the response corresponding to it is going to be faster. In other words, if a pole is more closer to the imaginary axis, or a pair of poles is more closer to the imaginary axis, the response of this pair of poles is going to take slower. Now, if we look at the transfer function, which appears something like this, so we end up having terms corresponding to each of the poles. If we take the step response of these, if we look at the step response of this poles, we end up having a response which generally will look something in this form. So it will be some constant term. It will have some exponential term which corresponds to how fast the decay of the complex poles happen, times sine and cosine terms plus some exponential terms corresponding to poles which are further away from the imaginary axis. You can imagine that as t increases, because the coefficient over here is larger, therefore these terms with the higher magnitude are going to decay to zero much faster compared to the rest of the expression. So if alpha is greater than zeta omega n, if alpha r is greater than zeta omega n, then as T increases, as T increases, as T increases, e to the power minus alpha RT will be much smaller than e to the power minus zeta omega nt, which basically means that these terms which are corresponding to uh, poles which are located further away from the imaginary axis are going to decay much faster. So in the end, the response is going to be dominated by whatever is the pole which is closest to the imaginary axis. So if it is a pair of complex conjugate poles, we'll end up having a response which is going to be dominated by a pair of complex conjugate poles. If it was just a real pole, then the same thing will hold true. So it will just be dominated by an exponential term which is corresponding to the real pole. So in this case, if we have the original transfer function, which is a higher order transfer function, then we can just approximate it by a second order transfer function, which is looking like this. Notice over here that both this transfer function Ts as well as the approximated transfer function, as well as the original transfer function have a gain of 1. So the way the gain of 1 is chosen is basically we have the system gain is k over here. So if you look at the transfer function, we have basically second order term. This has a system gain of 1. Similarly, the first order term that we have chosen is also having a system gain of 1. So the overall system gain is basically just the product of these two system gains, and that also remains to be 1. You can also find out the system gain by using the final value theorem for a transfer function response for a unit step input. So whatever is the steady state value for a unit step input for these transfer functions is going to be the system gain. So let's consider an example. So in this example, the original transfer function, the second order transfer function that is considered is this one, T1. So in this case, we are considering two transfer functions, which are third order, T2 and T3. And these two transfer functions are created by just multiplying a factor. So in the first one, for T2, we have just multiplied T1s times three over s plus 3, and T3 is T1s 10 over s plus 10. We can see that if we compare the response of these three transfer functions, we can see that the response of y1 is given by the blue curve. The response of y3 is given by the green curve, which is having a pole at s is equal to 10. And the response of y2 is given by the red curve. So you can see over here that y3 is following the response of y1 more closely compared to y2, which is happening because the pole is located further away from the imaginary axis compared to y2. So this pole, the pole at s is equal to minus 10 is much faster compared to pole at s is equal to minus 3. In general, when we are trying to come up with lower order approximations, we use a rule of thumb that we can approximate using a lower order transfer function if the dominant pole is 5 times, is having a magnitude of, if the poles with the higher magnitudes are having at least 5 times the magnitude of the dominant poles, then we can neglect those higher order poles. So in this case, if we are considering, so we can basically look at the magnitude of the real part. So the magnitude of the real part, let's say, is negative zeta omega n, and we consider the real pole at negative alpha r. So if we have this distance, which is alpha r, this distance which is zeta omega n. So if the distance from the imaginary axis compared to the dominant poles is 5 times or more, then we can neglect the poles which are further away. So in this example that we studied, we can think about what is the can we identify what is the real part of the poles for the complex conjugate poles. The real part of the complex conjugate poles, notice, is given by zeta omega n, which is related to the coefficient of the s to the power 1. So coefficient of s to the power 1 is 2 zeta omega n. So from that we can read the value of the real part of the pole, which ends up being that in this case zeta omega n for this example is equal to 2. So we can see that in this case T3 follows the rule of the thumb that it has the faster pole, which has a magnitude of 5 times the dominant pole. So we can assume that y1 is a good approximation for the higher order transfer function T3, but it is not a good approximation for but the response y1 is not a good approximation for the response coming from the transfer function T2, which can also be seen by these plots. The last thing that I want to describe is the topic of performance indices. So this is coming from the Doff and Bishop chapter 5.7. So you can find more details in this reference book. These different performance indices are just some of the performance indices that you can find. There are many other ways of coming up with performance indices also. So you can read up more information about it in Doff and Bishop. This is not an examinable topic except for knowing what a performance indices is. So in previous discussion, I've described that the response characteristics, the response can be characterized by several characteristics. We can describe settling time, peak time, rise time, overshoot, steady state error, peak response. So all these characteristics are basically corresponding to one of the two groups of performance. They're either describing what is the speed of the response, or they're describing how close the response is to tracking a desired reference value. The idea of performance indices is that we can also come up with one measure which describes the overall performance of the system. The way that we create this one measure is by doing a weighted addition of these, how well we are tracking versus how fast we are responding to an input. So one of the ways that this can be done is by looking at the tracking error signal. So we can calculate what is an integral of a function of the tracking error signal over time. And if we try to make this integral go down to 0, or we want to have a performance index which is the smallest value of this integral or minimum value of this integral, then we have somehow tried to make sure that the speed of the response versus the tracking is both being taken care of. So accordingly, we end up having these different definitions which are based on the tracking error, like the integral square of the error, integral of the absolute value of error, integral of the time multiplied by the absolute value of error, integral of the time multiplied by the square of the error. So that finishes this flipped lecture. Thank you. This is the last flipped lecture from my series of the lecture topics. So for the other flipped lectures, Carl will be putting up the recordings. So thanks for paying attention throughout my portion of the lectures.